So this is 6.5 times 10 to the negative 7th, and this is in meters. So the first thing we did was we converted the nanometers to meters. Now, once we have it in meters, we can then plug into our equation up here to determine the frequency. So the equation says C is equal to wavelength times frequency. C divided by the wavelength equals the frequency. So the value for C is the constant of 3 times 10 to the 8th meters per second. And the value for lambda is what we just calculated over here, 6.5 times 10 to the negative 7th meters. Now, to do this again, we can simplify it out. We do 3 divided by 6.5. And we do 10 to the 8th divided by 10 to the negative 7th. If you have your calculator, the trick I use in solving these problems is your calculator will do the tough simplification math for you. I like it. Some people like doing the math in their head. This right here times 10 is the EE button on your calculator, or EXP for those of you that own a Casio. Usually it's one of those two buttons. There's a few exceptions. So if I was going to enter this on my calculator, you do 3EE8 divided by 6.5 EE negative 7, and the negative has to be a small negative, not the subtraction sign. This gives us a numerical answer in our calculator of 4.615 times 10 to the 14th. Most calculators don't have a times 10 to written in there. It just has it raised to the 14th power. What it means is it is 4.615 times 10 to the 14th power. Now, this is what it's called the frequency of the light. You'll notice this is a really big number. That's okay. It's meant to be. And the units for this are meters, and meters cancel, leaving us with 1 over seconds. The unit 1 over seconds is called the hertz, like the car company. And sometimes it's also written as seconds to the negative 1, or inverse seconds. So you may see these units. These 3 units are all representing the same idea, the same unit. Frequency is also referred to as cycles per second, or how many times something happens per second. So this light with a wavelength of 650 nanometers, every second, 4.6 times 10 to the 14 waves pass by a location. It's a lot of waves. Really big number. A lot of waves. So that is how we could calculate the wavelength of red light. The frequency of frequency of red light from its wavelength. Questions or clarifications on these 2 steps? There's 2 steps to solve this problem. Any clarifications where I got anything from? Okay. And I'll give you some time to think about it. We're going to use this and see what else can we do with a problem like this. Okay. The great thing is once you have the frequency that you solve for here, can you calculate the energy, the top equation? Yeah, if you know H, you just take this number and multiply it by the H, which is another constant called Planck's constant, and that will give you the energy. So let's see what it looks like to calculate this last one here. We've got the frequency. The energy is equal to Planck's constant. So let's see if I've got it here. There we go. Energy equals Planck's constant times frequency. Planck's constant, we can look that up as 6.62 times 10 to the negative 34th joules times seconds. Got really weird units, that's okay. And then the frequency was the value we just got, which was the 4.615 times 10 to the some big number. 14 today. and that's in hertz, or 1/seconds. Now again, this is another problem. You can simplify it. When you're multiplying exponents together, you just add the exponents. So one way of doing this without a good calculator is 6.62 times 4.615. This equals 30.55. And then if you add negative 34 to 14, what does that equal? 10 to the negative 20. And the seconds cancel out. So this here is one possible answer for the amount of energy. Usually scientists convert the number so it looks like something like this. So this is the number 30, so you change that, you move the decimal one place over to the left, and this gives you 3.055 times 10. And when you move the decimal place to the left, this number increases by 1. You add 1 to negative 20, and what does that give you? Negative 19. That's the tricky math part. And this is your energy answer for the amount of energy in this red light. 3.05 times 10 to the negative 19th joules. Yes, sir. Yes, sir. So this is how to get the amount of energy in red light. Yes. The what? The J. Oh, the J. J is a unit of energy. We will learn more about this when we get to our fire unit. It's called joules. It's just a unit of energy. Right now, unfortunately, this number is like really small. This is a big J. How does it relate to life? Well, Bohr used these numbers, and he compared red light to blue light to see what their difference was. And the difference in the wavelengths, he was able to calculate where the electron would be found around the nucleus. So this calculation is just one of the things he did. We can do it here. We don't have to be like super Bohr man, but we can do it here. It's not easy, but it's something we can definitely try to do. So we're going to try to see what would happen here if we had a different color of light. So what I'd like you to do is work in a group of 4 people, 2 at the smallest, 4 at the greatest. I would like you to work with a group of 4 people and together come up with what is the energy of light with a wavelength of 475 nanometers? And would this light have more energy or less energy than red light? So what I'd like you to do is, we just went through a sample problem like this with a different color, different wavelength. Do the same problem with this information here. So please join with a few other friends and work together. We'll give you about 5 minutes to come up with an idea or an answer. Yeah. The first thing we had was nanometers. So it was big, 4.75. Based on 4.5. So that we got into meters. The second step, this is second step is solve for that. That's number there. We put this number there. 4.75 to the so know this you just got, and this that's your variable.